Hey, AP Chemisters, this is Mrs. Vanderlei bringing you Blankwalle 17.4. This is heat transfer and changes in the entropy of the surroundings. Earlier, we were talking about the entropy of the system. Now we want to talk about the entropy of the surroundings. What else we can talk about is heat transfer, the idea of Q, the idea of enthalpy. All right, so we learned earlier for a given change to be spontaneous, the delta S of the universe must be positive. That's your second law of thermodynamics. That's your excuse why your room might be messy. All right, you're just helping out the universe becoming more disorderly. All right, so what is delta S equal to? What is the universe equal to? If you recall back in chapter 6, we had two things we're looking at, the system and the surroundings. So the delta S, the system, will be part of the picture, and the rest is delta S, the surroundings. We add a little SURR because I think they got cut off. So if liquid water freezes, that's my system. What's happening to the delta S of the system? Going from a liquid to a solid. So what's happening there? Hopefully you know it is. Hello? Decreasing, that's right. Why is it decreasing? You're going from a liquid to a solid, becoming more orderly. So notice my energy bar is down in the negatives. So what's happening to the delta S of the universe? It's increasing. Why? Because of the second law of thermodynamics. It says in any spontaneous reaction, and yes, water freezes spontaneously, the entropy of the universe is always increasing. So look at my energy graph right here. My universe is a positive value. It has to be, otherwise it's not spontaneous. So what about the surroundings? What's going to happen there? Well, if the system is negative and the universe is positive, what must the surroundings be? It must be increasing. Why? For in order for the universe to increase, the surroundings must be a greater positive value than the delta S is negative. So if I go back and look at my energy bar, notice that this blue line is actually bigger than the green line because the overall magnitude has to be bigger than the system for the universe to be positive. Okay, so let's go ahead and see the next page. All right, so let's talk about how this becomes big and positive, all right, at least big enough to overcome the system being negative. So it says exothermic reaction in a system at constant temperature will increase the entropy of the surroundings. Think about that. What is freezing water? Isn't that exothermic? You're going from a liquid to a solid. It has to release energy in order to do it. That's exothermic. So what's it doing? It's increasing the entropy of the surroundings. It's giving more energy to the surroundings, so they're going to have more motion. It's going to increase. Endothermic reactions in a system at constant temperature will decrease the entropy of the surroundings. Why? Because they're taking energy from the surroundings into the system, and therefore the motion is going to slow down and you're going to decrease it. So it says, why does water spontaneously freeze at low temperatures then? So it's not just the fact it's exothermic is increasing it, all right, but why is it going to spontaneously freeze at low temperatures but not at high temperatures? So temperature has something to do with how disorderly, how random that is, okay? So this is kind of where we're at right here. So notice that if it is exothermic, okay, in both cases, that the surroundings is going to be positive, that's true, but it's going to be large at low temperature, so there's going to be a lot more disorderliness at low temperatures, and it's going to be positive and small at high temperatures. That's a little bit counterintuitive, isn't it? You would think at large temperatures, you're going to have a whole lot of disorder running around. And at low temperatures, you're going to have a little bit. It's not the absolute, it's the change in the entropy. It's the change in disorderliness. So I found a passage in your textbook I think describes this really, really well. This is found on page 825 in your textbook if you either want to read along or go back and refer this at another spot. So let me read this to you. It says, the greater the temperature, the smaller the increase in entropy for a given amount of energy dispersed to the surroundings. That's this bottom part here. So at a high temperature, it said, the smaller the increase, the change in the entropy. It says, recall that the units of entropy are joules per Kelvin. Energy units divided by temperature units. Entropy is a measure of energy dispersal per unit temperature kelvins. The higher the temperature, the lower the amount of entropy for a given amount of energy dispersed. We can understand temperature dependence of entropy changes due to heat flow with a simple analogy. I like this analogy, by the way. Imagine if you had $100 to give away. I wish. if you gave the $100 to a rich man, the impact on his net worth would be negligible because he already has so much money. So the change in his wealth didn't change that much. If you gave the same $1,000 to a poor man, however, his net worth would change substantially because he has so little money. So his net amount has changed significantly. The change has changed significantly. Similarly, if you disperse 1,000 joules of energy in the surroundings that are hot, the entropy increase is small. Why? Because the impact of the 1,000 joules is small in surroundings that already contain a lot of energy. So they're talking about the change is small at high temperatures. All right, so if you disperse the same 1,000 joules of energy into the surroundings that are cold, however, the entropy there is large. Why? Because the impact of the 1,000 joules is greater than the surroundings that already contain only a little bit of energy. For this reason, the impact of the heat released to the surroundings by the freezing of water depends on the temperature of the surroundings. The higher the temperature, the smaller the impact. All right, I really like that analogy to help explain what is going on right here. All right, so let's explain the S surroundings. So in order for the S to be positive enough to overcome the system being negative, the temperature needs to be low. Again, what do these deltas mean? The change in the entropy of the surroundings. Okay, so you need to have the low temperature so the energy added to it will change that entropy significantly enough to overcome your negative delta S of the system. Okay, so let's look down here. So again, the universe is equal to system plus surroundings. So at low temperatures, what did we just say? The change in the entropy of the surroundings is going to be a large value, at least large enough to overcome your system. But what about if you're at high temperatures? What's the change in then of the entropy of the surroundings? Not much, okay? You're given energy to the surroundings that already have a lot of energy. Your change is not great enough positive to overcome this, and it's the universe is going to be negative. So what's wrong? It's not spontaneous. So I wrote then, if the absolute value of the change in surroundings is greater than the absolute value of the change in system, oops, I spelled system wrong, didn't I? Then the universe is positive, it is spontaneous, and the opposite is true over here. Let's go on to the next page. All right, so let's recap this. A process that emits heat into the surroundings, this Q is negative, okay, increases the entropy of the surroundings, okay? So that means the delta S of the surroundings is positive. Okay, the process that absorbs heat into the energy where Q is positive decreases the entropy of the surroundings, therefore negative or delta S surroundings is negative. Notice what's happening. The signs are opposite. Did you catch that? The signs are opposite. So if it is exothermic where Q is negative, delta S of the surroundings is positive. The opposite is true. If it's endothermic, so that Q is positive, you end up with a negative delta S. That is really important to understand that the signs are opposite. Don't forget your negatives. All right, we've seen that before. Then it says the magnitude of the change of entropy is proportional to the magnitude of Q. And so here it is. I've already read to this. It's the quantity of heat over the temperature in Kelvin. Okay. So for an exothermic reaction, the delta S surroundings is positive. Why? Because it's the opposite of an exothermic. So what do two negatives make? A positive. Okay. So what about over here? The S of surroundings is negative. Why? Because the quantity of heat is positive, and so it's the opposite sign. So if you want to put this all together, all right, the delta S surrounding is equal to the opposite of the delta H in joules divided by the temperature in Kelvin. So it says consider the combustion of propane. Here is my reaction. Here's my delta H. It's very exothermic, by the way. All right, so calculate the delta S of the surroundings at 1 atm, then the system, and then determine the sign. Okay, so let's try this. What is my equation for the delta S? So the surroundings, the change in surroundings of entropy is negative delta H of the reaction over temperature. Temperature must be in what? In Kelvin. So here I have this, and that's what I end up getting. If you want it in joules per Kelvin, it would be 6,860 joules per Kelvin. But the important thing here is it's a positive sign. So the surroundings is getting more disorderly. All right, what about letter B? Calculate the delta S of the system. Well, what's happening? I have gas, 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 gas. That doesn't help me. I have 6 moles of gas becoming 7 moles of gas. All right, so what's happening to my delta S of my system? It's increasing. So now what? Determine the sign of the entropy change for the universe. Okay, well, here's this. And what was my system? Well, it's just a positive number, isn't it? Okay, I don't know what it is, but it's a positive number. Surroundings is positive 6.86 kilojoules per Kelvin, but I don't even care what that unit is. If I add a positive to a positive, don't I get a positive value? And what does that mean? Is it spontaneous? Yes, it is. Why? Because the delta S of the universe is positive. All right, so in problem number 4, here is another setup. Why don't you pause this and come back and see how we did? All right, so the delta surroundings is negative delta H reaction over temperature, excuse me. So it is the opposite, the negative. Let me scroll up here. So it's positive 163.2 kilojoules, so it's the negative of that. Because it's absorbing the energy from the surroundings, so taking away the energy from the surroundings, giving it less motion, right? So it's going to be negative 0.548 kilojoules per Kelvin. So if you want to be negative 548 joules per Kelvin. What about the system? I'm going from 2 moles of gas or 3 moles of gas to 2 moles of gas, so the system is negative. So about the universe? Well, system is negative, surroundings is negative, the whole thing is negative. So is it spontaneous? No, it's not. So that is the end of section 17.4. I'll leave you with this thought. Don't wait to be great. Talk to you later. Bye-bye.